Okay, geometry students, here is the Unit 3 review video that I promised you. I'm going to run back over the lessons real quick. If you remember way back, we started off with looking at angles formed around transversals. Okay, now we got a definition for the word transversal. Transversal is simply a fancy word that means a line that intersects two or more lines. Hopefully you should be very familiar with that after doing the city planner project. Okay, so I gave you some examples of transversals in the diagram there, and remember that there can be more than one transversal in a diagram at one time. When a transversal intersects two lines, there are angles that are obviously formed around the intersection. And as a matter of fact, every time two lines run into each other, we end up with 4 angles that are formed. So when you have a transversal, you're going to get a minimum of 8 angles that are formed. And there they are, 1, 2, 3, 4, 5, 6, 7, and 8. Now, the different angles that are there can have different categorical names depending on where they are positioned around the transversal. So on this first day, that is what we were doing. We were trying to get the vocabulary to name the different angles' positions. Corresponding angles. Corresponding basically means existing at the same general location but at different intersections. So we said like angle 1 and angle 5 in this case would be corresponding angles because they are both up and to the left from their intersections. Angle 2 and angle 6 are both up and to the right. Angle 3 and angle 7 are down and to the left, and so on. The word corresponding does not mean anything about the measurements. It only refers to the locations around the intersections of the transversal. The second type of angles that we looked at were called alternate interior angles. Okay, now alternate interior means, first off, alternate is referring to the transversal, so wherever your transversal is. Alternate means one angle will be on one side of the transversal, while the other will be on the other side of the transversal. Interior refers to the space that is in between the two lines that are intersected by the transversal. So in this case, the angles 3 and 4 and 5 and 6 are on the interior space. Alternate would mean opposite sides of the transversal. Okay, but again, that is only how to find a particular angle pair. That does not tell us anything about their measurements yet. Same side interior angles, same basic breakdown. We are still on the interior space between the two lines, but same side means that we are now on the same side of the transversal rather than one on one side and one on the other. Okay, they are also sometimes called consecutive interior angles. That's a synonym, same side interior, consecutive interior. And once again, these names do not mean anything about the measurements of the angles, only the positioning of the angles. Alternate exterior angles, these are the only pair that we have that are on, both of them on the outside of the two lines that are being intersected. Okay, so alternate, once again, means one on one side of the transversal, the other on the other side of the transversal, and exterior means outside of the space that is along the transversal. Okay, so again, that does not tell us anything about the measurements, only their positioning. Now, there is only one catch to all of this. You cannot jump from one intersection to another without the aid of a transversal. So while we can use these terms on the intersection where angle 1 is and the intersection where angle 2 is, we can use these terms between the intersection on angle 2 and angle 3. We cannot, however, use these terms jumping from the intersection by angle 1 all the way over to the intersection by angle 3 because there is no transversal connecting those two locations. Okay, so that was what we looked at on the first day. On the next day, we started to look at the relationships around those intersections, but this time allowing the lines to be parallel to each other. Okay. Now, if the lines are parallel, certain rules start to apply to the measurements of the 4 different angle types that we talked about on the first day, but only if the lines are parallel. And the rules were pretty straightforward. It just requires you memorizing which ones are which. Okay, corresponding angles. Okay, if your lines are parallel, then your corresponding angles are going to be congruent to each other. If your lines are parallel, your alternate interior angles are also going to be congruent to each other. Your same side or your consecutive interior angles, these are the oddball of the group. Your same side interior angles are going to be supplementary. And the way I told you to try to remember this was all the S's were going to go together. Same side supplementary, same side supplementary. The final set was the alternate exterior angles, and they are congruent to each other, once again, only if the lines are parallel to each other. Okay, the rest of this was looking at some diagrams. We talked about a bunch of different ways that we can move information throughout the diagram without messing things up, things like linear pairs and vertical angles and things like that, in order to be able to write an equation so that we could solve our problems. Okay, so you got to pay close attention, make sure you get the correct equation set up, otherwise you will solve for the variable incorrectly. Okay, on the next day, we turned the rules around and looked at the converses of those parallel theorems. The rules we were looking at yesterday said if your lines were parallel, then certain things started happening with your measurements. The converse would be if certain things are happening with your measurements, then your lines are going to be parallel. So basically, the rules read like this. Okay, so if your corresponding angles can be proven to be congruent, then that means your lines are parallel. Now, that doesn't mean you have to go get all of your sets of corresponding angles. If you can find any one set of corresponding angles and find out that they are the same measurement, then your lines are going to be parallel. Okay. The next converse is dealing with your alternate interior angles, and it says if you can prove that any set of alternate interior angles is congruent, then that means that your lines must be parallel. Same side interiors, remember same side interior or consecutive interior are the ones that are different. They are supplementary. So if you can find any set of same side interior angles that are supplementary, then your lines are going to be parallel. Okay, and the fourth of the four rules is the alternate exterior angles. If you can find any set of alternate exterior angles and prove them to be congruent, then that means that your lines must be parallel. Okay, the next thing we did is we switched gears a little bit and started looking back at some old Algebra 1 skills because we were getting into a discussion of equations of lines. So there were some basic skills that we needed to look at. The first one we looked at was the midpoint formula. Okay. Now, some of us are still struggling with this. Remember that any point that exists in the Cartesian Coordinate Plane, it aligns with the x-axis somewhere, and it aligns with the y-axis somewhere. Okay, when you take those two pieces of alignment and you put them together, that's called a coordinate, where it aligns with the x-axis, comma, where it aligns with the y-axis. And it is in that order, x, comma, y. It's alphabetical, so we should not have any confusion on that. Just remember that the x-axis is positive as you move to the right. It is negative as you move to the left. That's the way it's been all the way back to your number line in elementary school. The y-axis is positive moving upward, is negative moving downward, and where the two axes intersect each other, that is the origin. Its location is 0, 0. Now we're going to deal with a bunch of formulas and points that are in our graph. So what we've done is we are going to label our different points as point 1 and point 2. And remember that point 1 will exist at x1, y1. Point 2 will live at x2, y2. That's important because it's very easy to get the information confused, and you absolutely cannot take x information from one point and y information from the other. But we have a formula to find the midpoint between any 2 points that exist in the graph. And in plain English, the midpoint formula says you're going to take the average of the x values, comma, the average of the y values. And they are in parentheses because this is a point. Okay, so it's going to be a coordinate. So absolutely in parentheses with a comma in between them. Okay, so we looked at a couple of different ways of using the midpoint. This is the straightforward way of doing it, where we have two coordinates and we are asked to find the midpoint. The two strategies we're going to use and have been using all along is to take our 2 points and label them, x1, y1 and x2, y2, and we're going to write down our midpoint formula without anything plugged into it. Okay, then you plug your values in. We're going to simplify the numerators first, and then possibly look at combining with the denominators in order to end up with our midpoint. So we looked at a couple of examples like that, and then here is another way the midpoint formula can be used, and it can be used to do this. Instead of giving us the two endpoints and asking us about the midpoint, they can give us an endpoint and a midpoint, and then ask us to come up with the other endpoint. And the key or the catch to this one was to kind of figure out, as you move from one endpoint to the midpoint, the x value is changing by some amount, and the y value is also changing by some amount. If we can figure out how much those two guys are changing, then we can change them again as we move from the midpoint to the other endpoint, and that will give us our coordinates for the other endpoint. The next thing that we got into was a discussion of the concept of, actually this wasn't next, hold on just. Okay, I believe I've got it back in order now. The next one that we did look at was the distance formula, not the slope formula. Okay, so distance formula was again another one back from junior high, and this one is the big nasty radical that's down at the bottom of the screen right now for any points, point 1 at x1, y1, and point 2, x2, y2. There is a line segment that will connect 2 points, and the length of that line segment is found by this. Now in plain English, that formula says it is the difference of the x values squared plus the difference of the y values squared. And that result is all underneath a radical, or what you guys may know as a square root. Okay, so we talked about a little bit some things about distance. Remember that there is no such thing as a negative length or a negative distance, and it makes sense when you get to looking at the formula, because look at the formula. The difference of the x's is going to be squared. Squaring something means to multiply that thing times itself. So whether it's a positive number or a negative number, when you multiply it times itself, you're either going to get a positive times a positive or a negative times a negative. In either case, the result of that multiplication will be positive. Same thing with the difference of the y's. Since it's going to be squared, positive times a positive will be positive, negative times a negative will be positive. So you're always going to end up with positive values coming out of the distance formula. There's no such thing as a negative length. Okay, so this is just like with the midpoint formula. We've got our 2 points, x1, y1, and our x2, y2. We're going to plug in the values where they go. And as far as the math is concerned, you simplify inside of the parentheses first, then we square the values, and then we add those results together. Whatever that result is still underneath the radical. So if it is a perfect square, we will simplify it into a whole number. If not, we can convert it to a decimal using our calculators if we need to, but other than that, we'll leave it as a radical until we learn how to work with it better later on. Okay, now on to slope. Again, another junior high topic, but it is opening up a bigger discussion on equations of lines. Okay, so on equations of lines, we're going to learn that the slope-intercept form is y equals mx plus b, and that controls basically everything that the line needs to know about what it's supposed to do. Okay, and the equation of the line is going to give the line 2 pieces of information. It's going to tell it where to start, and it's going to tell it then where to go. Okay, where to start is the y-intercept. That attaches the line to our Cartesian coordinate plane. Everything else is based upon the slope value, m. Okay, so we're taking a look at slope, and we found out a lot of things about slope. First off, a lot of synonyms to do with slope. We could use the word slope or the algebraic variable m, like y equals mx plus b. Junior high had you doing a lot of rise over run vocabulary, so you could see rise over run there. The gray guy there on the left-hand side, y2 minus y1 over x2 minus x1, that's the formula that we use to calculate the slope in between 2 points. In written form, change in y over change in x. In Greek notation, delta y over delta x. Remember, delta means change, so that says change in y over change in x. And of course, the vocabulary I told you that they've kind of fallen in love with recently is rate of change. Okay, now a lot of information can be told about slope from reading the value. First off, of course, slope is a fraction, whether it is written as a fraction or not. The numerator is referring to the rise of the line. The denominator is referring to the run of the line. So it doesn't do us any good to change slope into a decimal because the fraction is actually needed. We need to know the numerator. We need to know the denominator. If that fraction happens to be a positive value, that means that the line is going to rise up as you move from left to right in the graph. And if it is a negative number, that means the line is going to fall as you move from left to right in the graph. Okay, slope really wants to be a value of 1, meaning 1 over 1, but of course those values are going to change for different lines. As the 1 over 1 changes, if it becomes a value that is larger than 1, meaning the denominator would be bigger, it's rising faster than it is running, obviously that's going to cause the line to stand up taller, more like the y-axis. But if it's a value that's smaller than 1, meaning the denominator has gotten bigger, than the numerator, it's running faster than it's rising, that will make the line more shallow, more like the x-axis. Okay, a couple more situations that we might run into for slope. Slope might actually end up being 0 if the line is running but refusing to rise. That's what we call zero slope. And it might be undefined if the line is rising but refuses to run. Okay, and that's the difference between having a 0 in your numerator for a horizontal line or a 0 in your denominator for a vertical line. Okay, now the biggest discussion that we've probably had through this unit is the discussion on equations of lines. It's probably going to be very heavily favored on the test, so you want to make sure that you know how to deal with the problems dealing with equations of lines. Okay, so continuing on with slope-intercept form, we've already spent a good bit of time talking about slope, the m value. Okay, but on this day we were focusing more on b. Now we said that the variables x and y are part of the equation of the line, so they are not going to be eliminated from the equation, and they will not be substituted for in the final equation. Okay, so we're looking at b, which is somewhere to start. Now that's a pretty straightforward concept. Where does the line attach to the y-axis? But as we saw, this can be the harder of the information to actually solve for if it is missing. Okay, and we went over a bunch of examples. I'm going to skip basically to the hardest one that we did. Okay, and this is the idea of the slope and the y-intercept are both not provided for us in the problem. Okay, so when that happens, obviously we have a slope formula, y2 minus y1 over x2 minus x1. We can plug our points into the slope formula, and we can arrive at a slope fraction. That's not too much of a challenge. The real issue is, what do you do if the y-intercept is not provided for you either? Well, we already know what m is. X and y are part of the equation, and b needs to be found. Now, we don't want to eliminate x and y, but we would like to replace them temporarily so we can plug in and solve for the b value. So what we talked about is the fact that any point that we know for a fact exists on a graph, its point can be plugged into the equation from that graph. So that's what we're going to do. We have 2 points. We're going to select one that we like, and we're going to plug in to the equation using the x and the y from one of the points. So we selected the 1, -4 in class, and we plugged it in for x and y. And what that did was it left us an equation that only had a b variable in it. And when we solved for the equation for b, that allowed us to get a value for b, and we could plug in, and our equation was complete. Okay, and that finally brings us to the last lesson, which we looked at earlier today, which is the slopes of parallel and perpendicular lines. Okay, now we already know well by now that is the slope value of the equation that causes the line to behave in different ways. Okay, so if two lines want to be perpendicular to each other or parallel to each other, then it's going to be a comparison of their slope values that allows them to do those things. So 2 basic rules. If 2 lines want to be parallel to each other, then they must rise and run at exactly the same speed. That means their slopes must be equal. If they want to be perpendicular to each other, they're going to have to hit each other at a particular way. Got to form a right angle there. And the way that that happens is that the 2 slope values need to be negative reciprocals of each other. Now, negative reciprocals means if you take a fraction and turn it upside down and change its sign, you have just discovered the negative reciprocal. If the 2 slope values are negative reciprocals of each other, then your lines will intersect and form a right angle at the intersection. Okay, so we looked at some examples. Of course, if 2 slopes are the same, that means they are parallel, and there is a demonstration for you of negative reciprocals. Take one of the slope values, turn it upside down, and change the sign of the fraction. If that matches up to the other slope fraction from your other line, then you do have lines that are perpendicular. Okay. One very critical piece of information is dealing with your equations. Do not ever try to read slope or y-intercept out of an equation without getting your equation into slope-intercept form. They will try to catch you on this. I would be surprised if you saw this any fewer than 2 times tomorrow where your equation was not in slope-intercept form. You need to get it in slope-intercept form before you start messing with the math or looking at any slopes or y-intercepts. Convert to slope-intercept form and then answer your questions. Okay, so that is basically it. There's a lot of information in this unit. It's kind of spread out over a long period of time, so I'm glad you were able to find some time to take a look at the review video. Please study. Make sure that you not only know how to work with those equations of lines, but there's a lot of memorization that you need to do as far as the transversals and stuff like that. All right, I'll see you at the test tomorrow.